I'm going to talk about the four type of powers, which is very important for you guys as an optometry student. And I know 95% of students, even they are in fourth years, they don't know about these things because it's quite complicated, and there are a lot of stuffs background. You must have that knowledge to understand actually what means by back vertex power, what means by front vertex power, what means by effective power, what means by equivalent power and nominal power. So all the form of power we are going to talk: nominal power or approximate power, what is in front vertex power, in effectivity of the lens, and equivalent power, and what are the difference between them. Okay, let's move. For nominal power or approximate power, it's simple. There are two surfaces of the lenses. F1 is front surface lens power, F2 is back surface lens power, how we derive it, and S1 is n divided by r. And then we simply add each other because we don't consider thickness as a significant. So thickness is not significant in case of this. So we use this formula for thin lenses. It's simple, isn't it? It's very simple. We don't consider thickness as a significant uh, measure or significant variable. So we just add the surface power, and hence the final power is approximate power or nominal power. This is simple, and this is for thin lens. Finished. Let's move forward. Now we come to thick lens, and the equations become more and more complicated. Okay, thick lens does not have single focal length. It has several focal lengths. For example, two focal lengths I want to talk about is if equivalent focal length and focal length, or equivalent power and vertex power. See, in case of vertex power is always taken from the vertex, from the surface of the lens, isn't it? See in this picture, this is vertex power, this is back vertex power. From this vertex, front vertex focal point is front vertex power. But equivalent power is always taken from, as we discussed in the cardinal points, taken from principal plane, isn't it? From secondary principal plane to secondary focal length is equivalent focal length, equivalent secondary focal length. And from primary principal plane to primary point is what is this? Yes, is equivalent power. And equivalent power, we must take equivalent power from principal plane. And we know one thing: principal plane is imaginary plane, and it moves towards the more curved surface, isn't it? We have discussed already. You have to understand this. So it's not a fixed point. It's not a fixed point for every lens, but the vertex point is fixed, isn't it? So that's why, for the practical purposes, for clinical purpose, we do not use equivalent power for our spectacle lens. Okay, we do not use equivalent power for our spectacle lens. For a spectacle lens, in lensometer, we always calculate back vertex power, and not even for front vertex power. But yes, definitely sometimes in bifocal we use front vertex power, but maximally we use back vertex power. So it's why back vertex power? Because back vertex power taken from back vertex, which is simply then and there, and which doesn't move with the lens. But in case of principal plane, it moves towards the more curved surface. So it's quite difficult to measure uh, equivalent power. So in practically in clinic scenario, we use back vertex power. This is the answer. So sometimes in your viva, faculty asks this question, and you have to be confident. Okay. So back vertex power, just deal with the back vertex power and front vertex power. See, let me remind you the concept of downstream versions and upstream versions once again, and then we will understand what do you mean by back vertex power. See, I'm trying to explain the concept of downstream versions and upstream versions. Okay, so let's take example. This is the lens. Okay, and here we go. Light comes from infinity, and it focuses here, somewhere in between here. Okay, that's perfectly okay. If I want the versions at point A, and if I want a versions of point B, and if I want versions at point C, then all the point have different versions, isn't it? because from this point, this is, let's take an example, in 10 centimeter away, this point is 20 centimeter away, and A is 30 centimeter away. If this is the case, then we must understand vergence at different point has a different vergence, isn't it? In respect to B, A is upstream vergence because it's opposite to the direction of light. In respect of C, B is upstream vergence. But just remember this thing. In with the respect of A, B is downstream vergence because it's along the direction of light. And in respect to A, C is also downstream vergence. In respect to B, C is downstream versions, definitely. So in respect to A, B is downstream versions. In respect to C, B is upstream versions. So that's the case. So why it is important to understand downstream versions? Because effective power and back vertex power and front vertex power both are downstream versions. So let me clear up. Let's erase first and then I'll clear it off for you. See, let's take an example. This is the lens, front surface f1 and back surface f2, f1 and f2. So light, so let's take example. Light came from here. Okay, so it came from here, and for example, it refract and it refract less, and here's the focus. Okay, so what happens between this point, front surface, to this point, back surface? Isn't it downstream versions? And see, you feel similarity. Just try to remember the formula of changing the spectacle power to contact lens power. Isn't it this? F minus F divided by 1 minus df. Isn't it? So it isn't it, can you see this formula? Can you see any similarity? Because this formula is actually downstream versions formula. See, let me clear. F1 divided by 1 minus t divided by n into F1. It means what is the vergence of light when it strikes to F1 and travel t distance and reach to back vertex power. Here, what is the vergence of that surface, F1 surface, when light reaches here at F2? That means this downstream versions of F1 surface up to where? Up to traveling t distance, up to traveling this t distance. Obviously, t by n is reduced versions, reduced thickness, yes. And we add F2. Isn't it simple? So you have to understand what is it. It's the downstream versions of front surface till F2, and then you add F2. We don't have to calculate the downstream versions of F2 surface because light travel from front surface to back surface. That's why we call it as a back vertex power, because it power at the back vertex. Do you understand? Power at the back vertex. For front vertex power, light travel from this direction because we calculate power at front vertex, at front surface, not at back surface. So that's why light must travel from opposite direction. In this case, light travel from this direction. First hit front surface, then hit back surface at last. That's why it's called back vertex power, because we calculate power at the back of the vertex, back surface of the vertex. So it's central important to understand what do you mean by back vertex power. It means by this. See, this power of a front surface, not just power of front surface, downstream versions of front surface at back surface and add the back surface. You are not directly adding f1 plus f2. You are adding f2 plus downstream versions of f1 surface, which is t by n f1. So that's why this formula always contains f1, 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 and f2 is untouched in case of back vertex power. That's why in case of back vertex power, you are just free and just think only one thing. First, add f2, doesn't matter, then reduce versions of f1. This is reduced versions of f1 formula. Isn't it simple? So same goes with the front vertex power. See, in this case, it's quite funny. So this is f2 and this is f1. Light comes from here. It must be, because we have to calculate downstream versions of front surface, isn't it? Back surface, sorry, back surface. Downstream versions of back surface. For the downstream versions of back surface, light must travel in opposite direction. And I have told you, this is the direction of light. Then travels f2 divided by 1 minus t by n f2. What do you mean by that? Downstream versions of f2 surface. At where? At f1 surface. And then we directly add f1 surface. Finish. That's the front vertex power. So you must understand the concept of downstream versions to explain front vertex power and back vertex power. Front vertex power we sometimes call neutralizing power. Back vertex power we call prescribing power, because in the prescription, optometrists often write the prescription which is back vertex power. But when we do hand neutralization and find out the power which it's front vertex power. Front vertex power and back vertex power just differ to each other in a small power, like plus 1, plus 2, yeah, minus 1, minus 2, minus 3, minus 4. When it goes higher and higher, in case of plus 8, 10, 12, then the difference between front vertex power and back vertex power is significant. So we do not do hand neutralization in case of high plus power. There will be chances of fallacy. Okay, you understand this concept. I hope you understand this concept. It's a very important concept. So let's move further into equivalent power. What do you mean by equivalent power? See, what do you mean by equivalent in this term? See, equivalent power means when there is a multiple surface or only two surface, or thick lens or multiple thick lens, whatever. If there is multiple thickness, then thick lens or only thick lens with two surface and significant thickness, then we replace that system with only one surface. And what should be the power of that surface? That's the concept of equivalency. It means you replace this surface and you tell me one power of that system. What could be that power of the system? This is called equivalent power. So in case equivalent power, you always use equivalent power in case of low vision. It's very important to understand. In low vision, this formula comes again and again and again and again. See, f1 plus f2 t by n f1 into f2. I have already discussed of this, and the third term, it is central to understand this third term. And this picture I have put because I want to tell you that principal plane always move towards the curved surface, more curved surface. So it's very simple formula, but you use there. See, I'll give you an example. Use this formula and use this formula for the power of equivalent power of telescope. Can you use this formula? It always comes zero, isn't it? Equivalent power of telescope is zero. Why? Let me explain. If light comes parallel to objective lens of uh, telescope, this is objective lens and this is eyepiece, light goes parallel. So parallel light comes and parallel light goes. That's why whole system has equivalent power of zero. Isn't it? Telescopes have equivalent power of zero. So what do you mean by equivalent power? If you replace all the system with a one surface lens or one surface power or only one power, that's in that case you need equivalent power. And equivalent power is always measured in case of thick lens from principal plane. It's central important to understand equivalent power. So this formula and playing with this third term is very important. You tell everyone that I has a power of plus 60 or plus 61. Please put the power here and what happens, just see that. Okay, power of the cornea and power of the lens and the distance between cornea and lens, which is equals human, and the index definitely. So just put this and see what happens. Okay, Effectivity, I have made already one video in effectivity. Just go there and watch. But let me explain one thing. Effectivity means the, see, in this A picture and B picture, both picture has only one thing they want to do. They want to have minus lens, and they want to project the minus. Final outcome is to focus on the retina, isn't it? But it's not that. They have minus lens and its secondary focal point not in this space but in this space. See, this is the picture of contact lens correcting eye with, sorry, with power of 6.67 minus 6.68. So when the contact lens moves to spectacle, isn't it the upstream versions? Simple thing. Now why power increases in spectacle? Because now this lens has the responsibility to focus in this power point, because we know for subjective refraction, infinity, far point, far point of a secondary focal point, and secondary focal point, secondary focal point to far point, and this is the concept of uh, concept of subjective refraction, because the power must coincide, power secondary focal point must coincide with far point. So when we move this contact lens to spectacle, the distance between spectacle lens and the far point reduces, and when the distance reduces, power increases, isn't it? Power is 1 by f. The distance decreases and the power should increase. That's why spectacle power in case of minus lens is higher than the contact lens, and that's why exact opposite happen in case of plus lens. Because for plus lens, if let's take an example, this is a plus lens and we have to focus here, this is the distance, isn't it? And at the same time, when we put contact lens closer distance, the distance reduces. In case of contact lens, the distance reduces. That's why power should increase. In case of contact lens, uh, spectacle power is higher than contact lens power. But you can view as a downstream versions too. It's central important to understand this concept that for subjective refraction, spectacle secondary focal point must coincide with the far point. And when you move that spectacle to contact lens or contact lens to spectacle, it doesn't matter. What happens with the distance between far point and the lens or contact lens? If it reduces, then the power should increase. If it increases, then the power should decrease. That's the game of effectivity. You must understand. For effectivity, you must understand the concept. For subjective refraction, for to see clearly, the secondary focal point of correcting lens must coincide with far point. This is the concept. It's central important concept. Okay. So, and finally, just remember when you are saying back vertex power, which is prescribing power, or front vertex power, which is neutralizing power, just remember that F1 divided by 1 minus T divided by N F1 is always downstream versions of F1 surface towards F2 up to F2, and in this case downstream versions of F2 surface up to F1. That's light, and in both cases light direction of light is different. So it's very important clinically, back vertex power and front vertex power. Equivalent power, we replace all the system to one power, and that's how much power it is. So it's called equivalent power. So location of the principal plane, I already told you, you can use this formula and locate there. And effectivity, you must understand, and I have told you, for to change the from spectacle to contact lens, f minus f divided by 1 minus df. So d in air, that's why we don't use 1, isn't it? This equation and this equation is same. So both equation are downstream versions equations, central important to understand. Okay. So again, just start with this book. This is a great book, and this is also a good book. Don't forget. And my favorite book. Okay, just remember these three books are golden books. You can understand optics, and when you understand optics, you will become a better optometrist. Okay, for now, uh, auf Wiedersehen. Bye bye.